Another type of differential equation is called the homogeneous equations. These homogeneous equations are not separable. You cannot break up the x and the y individually. So some of the examples will be things like this, which you have, there is no way for you to separate the x and y, or that, not that you can break up the tangent x and tangent y, or you have expressions that seems like you cannot break it up at all. These differential equations are sometimes called the first order differential equations. First order as in you are dealing with y prime. There are also something called second order differential equations which involve double prime in your equation, but in HL you don't need to learn that. The maximum order will be first order. And homogeneous equations, if you cannot separate them, we need to make other substitutions to make it work. The most common substitutions for homogeneous equation is y equals v times x. Y equals v times x. On the IB exam, this is the most common substitutions for homogeneous equations. If you need other substitutions for your homogeneous equations, they will tell you what substitution to use. Otherwise, you will always be using this substitution here. Now with y equals vx, as you make your substitution, your dy dx will turn into something else in terms of v and x instead. Using product rule, your dy dx will then turn into these two terms. Or, as you simplify dx dx, your second term will simply turn into v. Or some people would like to differentiate this sign instead, and some people would use quotient rule, but you can use whatever method you can to turn it into something like this, and you can then make a substitution using these expressions here. So in example number 1, when we have a differential equations with x and y not easily separable, we will then make use of this substitution here. And once again, v equals y over x will just be the same as y equals v times x. Or in another word, dy dx that you see here will now turn into something else. Using the product rule, you can see how dy dx will turn into this one. This is what we see. On the right hand side, with x squared plus y squared in the numerator, as you simplify it, multiply both the top and bottom by 1 over x squared, you will end up with something that is pretty convenient to work with. You will just end up with 1 plus v squared at the top, and the denominator will just turn into 2 times v. So this substitution would have simplified your equation a lot. And as you continue to go from there, moving the plus v to the other side, minus v, and get the lowest common denominator, bring them together, you can now separate the variables. So your substitution, y equals vx, make this equation separable. As you break up the x and v on each side, you can then integrate both sides. Use use substitution if you need to, integrate your expressions, and eventually simplify it to something like this. Now, some people don't like using this technique to simplify the equation because sometimes they just don't know what to multiply, what extra terms to multiply to both the top and bottom to make your expressions work at the end. If that's the case, you can simply substitute your y using v times x. Using v times x, using v times x, this is what you will end up with. And as you replace your dy dx using this part here, the right hand side, as you simplify your x squared, will just turn it into the same thing as before. And you can solve this differential equation using the same technique here.